Without scissors, I can't really do anything. I forgot. I usually install my system here for my student, and then my class is right after. It's okay. I'm gonna go borrow scissors from somebody. I thought I was all prepared. Okay, I guess I was.
Scissors in my own.
Yeah, yeah, it's okay. Yeah, thank you. Yeah, yeah, yeah. Okay, thank you. But you know what? I'm sure I can find the scissors at the library and I just cut it. Like over here and then install it for my class. Thank you.
Okay, so it says 7:30. So a couple of things before we get started. So did you all see that I posted homework 1 yesterday? Did you not see the
No.
email from Piazza?
It
It's what?
files.
But no one tell me. It's not super important because like I said in the, okay, did you get the Piazza message?
Yes, yeah.
Okay. So like I said in the Piazza message, it's not due anytime soon. And I was just posting it. I will upload it. But so just wanted to talk about it a little bit. So how many of you guys have used Gradescope in the past? Okay. How many of you guys remember selecting like what pages each question corresponds to? Okay, so you will not do that in this class. These PDFs that I am uploading to Canvas are fixed templates. So the space provided here for question 1, part A, is where your answer for question 1, part A will go. It will not go anywhere else. Same for B, C, D, E, F, and then same for question 2, question 3. You should not move these around. Because when you upload your completed homework to Gradescope, you'll have all your answers in the right places. And then Gradescope will show me exactly that part of the question when I'm grading that question. So it's a fixed template. So do not modify the PDF other than adding your answers. Are we all good with that? I always get maybe 2 to 5 submissions that are not fixed templates still. So let's try and not have that happen this time. And for the first homework, I will be lenient on it. I will still grade if it's not turned in as a fixed template, but I will put a note on your submission and Gradescope telling you if it's wrong. And then homework going forward, if it's not in the spot where it's supposed to be, it's just not there. Okay?
So I'm not super familiar with Gradescope, but so do we just submit that PDF with our answers in it and then that's it?
Yeah, that's it. So you just upload the PDF and just make sure that it's the same format. The questions are in the same places. So then my next question is, do you want the Word document for this? The doc file?
Yeah.
Okay. So be careful though. If I give you this doc file, I want it still in the same fixed format. Okay? All right. See if I can upload this now. That's still not uploaded. Okay. I need to share. Okay, the other thing is, I did post the poll results. Yes? I know those were posted because someone emailed me that they were missing, so.
For the lecture
Yeah,
participation.
lecture participation. Okay. So do check if you were here and you answered the poll and you changed your student ID to show up. If any one of those things were not true, it will be a 0. So if you need to make sure that you're responding as student ID, because I did look at it manually, there are still about 5 students not responding as student ID. So if that is you, then it is going to show up as a 0, do just tell me to change it because you didn't change your student ID yet, but do change it to your student ID for the future. Okay?
Yes.
Alright, so I think that's all for logistics. Oh, well, I guess I didn't finish talking about the homework. So the homework, I posted it, you can't do all of it yet. And ignore the due date on Gradescope. I will update the due date on Gradescope as well as Canvas. On the last day that we finish the content for the homework, you will have 1 week to finish the homework from that point on. Okay, so we are on performance still. And so we've kind of answered what is performance, and then we're talking about different performance metrics. And we are also still talking about how to evaluate performance with these metrics. Okay, so this is what we had from last time, right? CPU time is going to be the number of clock cycles times the time it takes for 1 cycle to execute. And then because cycle time is quarter circle of clock rate, you can substitute clock rate like 1 as cycle time. And then we answered these questions, right? How does the total number of instructions impact the clock cycles? Do the different types of instructions have different number of clock cycles, right? So, and this is not your checkpoint yet. It's just something that as review. So integer operations take longer than floating point ones. Is this true or false? False, right? Floating point formats is much more complicated. So the hardware to implement this is going to be much more complicated and therefore take longer. All right, accessing memory takes more time than accessing registers and cache. Yep, this is true, right? The registers and cache are at the very top of the memory hierarchy. They're the smallest, but they're the fastest. And then memory is below them. Okay. So it's a little bit, well, it's quite a bit slower, but it's also quite a bit larger, right? Okay. So back to the performance equation. So the number of clock cycles depends on the number of instructions in the program, right? The type of instructions in the program. Like we talked about, there are different ways that different types of instructions would take more cycles. For example, multiplication is going to take more time than addition. And we just talked about floating point versus integer. Memory instructions versus just arithmetic instructions. So we have instruction count. So the number of clock cycles is now going to be the instruction count times the cycles per instruction. And instruction count is just simply going to be the number of instructions for the program. This is determined by both your written program, the ISA, and the compiler. And then CPI, this is going to be average cycles per instruction. This is going to be determined by the CPU hardware itself. So the implementation of those instructions. So these different instructions are going to require a different number of cycles. So the average CPI of your program is going to be affected by the instruction mix of your program. So like what portion of your instructions are arithmetic instructions, what portion are memory instructions, what portion is floating points, what portion is multiply. So if all of those things have a different number of cycles required, then the portion of each one of them and their mixture is going to determine your overall average CPI. Okay, so then our equation with this new part substituted for clock cycles is CPU time is instruction count times cycles per instruction, CPI, times cycle time. So if we have it all written out in their units, and then again, we can substitute for cycle time clock rate, right? They are just reciprocals of each other. So any question on this so far? So here's our example one. So it takes a program of 1 billion instructions, 4 seconds to run on a computer with a 500 megahertz CPU. So what is the CPI of the program on computer A? Okay, so we have our equation. And we're given the clock rate, so we're going to use this equation. And then here we've just rearranged it to put CPI on the left side because we want to solve for CPI. Right? You see that this is the same equation. And now we have our CPU time is 4 seconds, right? Our clock rate is 500 megahertz. So mega is going to be 10 to the 6. And then we have 1 billion instructions. So it would be 1 times 10 to the 9. And we get, we use the calculator to solve this, 2. So our average CPI for this program on this CPU with this ISA is 2. So on average, 2 cycles per instruction. Okay. So again, this is not your first real checkpoint, it's just a discussion. Okay, so the same machine running 2 different programs will have the same instruction count and cycle time, but different CPI. So is this true or is this false? Let's just start one thing at a time. So it's same machine. So what does this mean?
Hardware.
Same microarchitecture. What else does this mean?
Same instruction set.
Same ISA. And then we have 2 different programs. So what does that mean?
Two different set of instruction.
And so what does that mean for, say, something like instruction count?
Likely it would be different.
Yes. And then let's go on to, so we already know that instruction count should be different because they're 2 different programs, right? So we already know that the answer to this is false. So let's just finish with cycle time. So does the 2 different programs impact cycle time? No, right? And what did we say? Because they're the same machine, they have the same microarchitecture. So because they have the same microarchitecture, do they have the same cycle time? Yes. And then different CPI. So is this true? Is the microarchitecture is the same, right?
Right.
So the different instruction types will have the same cycles needed for each instruction. But we have 2 different programs, right? And we mentioned that's going to affect instruction count, but it will also affect the instruction mix. Right? So what are the different instructions being used? So it's not necessarily true that they would have the same CPI. So this is false because of 2 reasons. They should most likely have a different instruction count and CPI. Are we good with this? So again, very similar question. So if we are running the same program on 2 different machines that have the same ISA, then instruction count and CPI will be the same for both machines. So again, here, let's just go one by one. So same program. What does this mean?
Same.
Same instruction count. And we have two different machines, but the same ISA. So we know that instruction counts are going to be the same because it's the same program and same ISA, right? Then we have two different machines. So what does this mean? Yeah. So if you have a different implementation of microarchitecture, what could that mean for your CPI?
Your clock could be different. But
So that would be cycle time. Okay. So
It would take each machine a different amount of time or a different amount of cycles to complete the instruction.
for different types of instructions, right? So like one could have optimized for say multiplying. And it takes 2 cycles to do a multiply instruction. Whereas another one might have optimized for floating points. And that one might take 3 cycles for multiplication. So because of that, the CPI could be different because of the underlying microarchitecture. So this is still false. Okay. So are we good with if we have program difference, microarchitecture difference, how these things could affect instruction count, CPI, and cycle time? So here's the last one. So we are running the same program on 2 different machines with different ISAs. Then cycle time, instruction count, CPI will be different. The same program, but 2 different machines with different ISAs. So 2 different machines, we immediately say what's about cycle time? Different, most likely different. Instruction counts, we have same program, right?
ISAs are different.
The ISA is different. So this will most likely also be different. And then if this is different, this is also most certainly different as well. Okay. So this one is actually so going back to our formula and adding our new addition of instruction count times CPI is clock cycles. And just to summarize all of these different acronyms, so IC is instruction count, CPI is clock cycles per instruction, and then CT is going to be your cycle time, CR or F, so that's going to be frequency, that's your clock rate. Right. So here is an example again. So we have computer A, clock rate is 4 gigahertz. And conveniently, this is just going to be cycle time is 250 picosecond. CPI is 2. Computer B, clock rate is 2 gigahertz. So cycle time is 500 picoseconds. CPI is 1.2. And we're saying they have the same ISA. The question is, which is faster and by how much? So this is your actual first checkpoint. And your code for today is 533. So just tell me once you have all this information. Basically, just look down when you have it.
Justin,
Okay.
what was it, 543?
533.
5 what?
33. 2 3. Okay, does anyone still need this part? Just uploading. Okay, so here's the PDF. Here's the document. Is anyone still working on this on their own? Okay, so we are not quite at threshold. Quite a few people changing their answer. So do talk to the people around you. See if you guys can. Do what it says.
I put feet at first, but I realized I was connected. Because.
Yeah.
Yeah. Right, yeah. Yeah, 500 small. Yeah. I'll go ice instructions. For icy items.
So we're done discussing. Do you change your answer if you were to miss? Change your answer. Have movement back to right answer. All right. So here is our information, right? So same ISA means same instruction count for the same program. Okay. So the question is, which is faster and by how much? And we're going to recall our performance equation as instruction count, CPI, cycle time, right? So we have CPI, we have cycle time, we do not have instruction count. So we can multiply these out, get an answer in terms of instruction count. Same thing for B, we have CPI, we have cycle time, we don't have instruction count. So what we get is A is instruction count times 500 picoseconds, and B is instruction count times 600 picoseconds. So A is going to take less time, right? So A is faster. And then we just need to put the larger number on top, right? Divide by the smaller number, and A is faster by 1.2 times. So if we go back to here, correct answer is A. A is faster by 1.2 times. Okay. So CPI can be expanded even further because, as we mentioned, if different instruction classes take a different number of cycles, like multiply instructions, memory instructions, floating point instructions, then you can calculate the total number of clock cycles by taking the summation of the CPI for that instruction time times the number of instructions of that type gives you the total number of clock cycles for that instruction type, right? And then if you do that for all of your different instruction types, you'll get the total clock cycles for the entire program, right? So this is instruction count for the I type of instruction class, and this is the average clock cycle per instruction for that I class. So from this equation, we can also figure out that we can find the average CPI by taking this weighted average. So the overall average CPI is going to be the total number of clock cycles divided by the total instruction. Okay. So basically, we just take this equation and divide it by instruction count. Because then that becomes clock cycles over instruction count, which is CPI, right? Do we see this? And then if we simplify it a little bit, we can see that we'll get the CPI of instruction type I times the instruction count of instruction type I divided by the total instruction count. So this is the relative frequency of that instruction. Right? So what percentage of my instructions is that instruction type? I can just take that, multiply it by the CPI for that instruction type, sum all of those up, then I get my average CPI that way. Do you see this? So here is an example. So hardware designers supplied the following CPIs for each instruction class, A, B, and C. Compiler is considering two code sequences that require the following instruction counts. So this is the CPI for the class. So A is 1, B is 2 cycles, C is 3 cycles. And then the compiler has two different paths that it's determined would result in the same correct program. But we want to figure out which path is better. So the path for sequence 1 requires 2 instructions from type A, 1 instruction from B, 2 instructions from C. The instruction count in sequence 2 is 4 of type A, 1 of type B, 1 of type C. So which code sequence executes the most instructions? So instruction count in sequence 1 is going to be 2, 3, 5 instructions total, right? Instruction counts in sequence 2, we have 5, 6 total instructions. So in sequence 2 does more instructions overall, right? Now the question is, which one would be faster? So for that, we need to figure out what's the real clock cycle, the number of clock cycles. So to get the clock cycles, I need to multiply CPI by the instruction count, right? So for sequence 1, for instruction type A, I have 2 total cycles. And then B, I also have 2 total cycles. So this is 4 cycles. And then C, I have 6. So 4 plus 6, this is 10 cycles total. Okay. And then instruction count in sequence 2, I'm 4 cycles for type A. And then 2 more for B. So 6. And then 3 for C. So I'm 9 cycles. So although I have more instruction count in sequence 2 is still faster. And then we can also calculate the overall CPI for each sequence. So we found this was what? 5 instructions and 10 clock cycles. So this is this overall CPI of. What's my number? What's CPI?
The average clock cycle per instruction.
So I need to take clock cycles divided by instruction count, right? So clock cycles was 10, right? Instruction counts was 5. So CPI is 2. Okay. And then here we had 6 instructions, 9 clock cycles. So 9 divided by 6. So this is going to be a lower CPI. So this is just what we just did, right? We calculated instruction count, we calculated clock cycles, and then here is our CPI, right? 2.0, 1.5. We all good with this? Okay. So this is your next question. So given these different instruction types, their CPI for that instruction type, the frequency that they occur in a program, what is the average CPI? And do this on your own first. Even people still working on this. You're close to the threshold, but not quite there. So do, again, talk to the people around you, walk through how you got to your answer.
I tried. But I don't. Yeah, right. First CPI. And then add it there, and then I went through it again, and now. Two times, which is what we every two times. No Pico or good on my end, use me again notifications.
Yeah, the first one is just 0.5, right, for the formula. And two.
That's none of them. Your discussion dying down, so do change your answer. Okay, and more of you are changing. Right. So how are we gonna do this problem?
The other nine about
This CPI times the frequency for each instruction type, and then sum them all up. Right? So here it is. This is the equation that we just looked at. And so ALU is CPI of 1, frequency 50%. So 1 times 0.5 gives me 0.5. 2 times 0.2 gives me 0.4. Again, 2 times 0.2, 0.4. And then 2 times 0.1. That's good. Add it all up, I get 1.4. So correct answer is B, 1.5. Right. So those are fairly simple examples. Here we can see a little bit more complex of an example. So we have a program on a computer with 2 passive instructions. CPI of the first instruction is 2, CPI of the second instruction type is 4. So what's the overall CPI of this machine? Same as before, right? So 2 times 0.4, and then 4 times 0.6, add that up, I get 3.2. But what if we ask if the CPI of the instruction class B is reduced to 3 without changing the clock rates? How much faster is the new machine? What is the CPI? The CPI new is, so A didn't change, right? So 2 times 0.4, but B changed from 4 to 3. So now our new CPI is 2.6. And then the other thing that we have to ask ourselves is what's changed about instruction counts and cycle time, right? So we just reduced the CPI of B from 3 to 4, and we also mentioned in the question that clock rate does not change, right? So clock rate does not change, so cycle time doesn't change, right? So cycle time old is same as cycle time new, so they cancel. And then we didn't change our ISA, right? So on the same program, instruction count old is instruction count new. So those cancel. So in this case, the speed up is just the ratio of the CPU. Okay. So we get 1.23 times faster by doing it. And then what if we reduce the number of class A instructions by 50% of the original for the program? And we still have the CPI of B is reduced to 3. Then how much faster is the new machine? And what's its CPI? So this is like old instruction count. This is new instruction count. So we're just going to assume there are originally IC instructions. So like this is instruction count old. Then the clock cycles from our previous answer is 3.2 times instruction count. And then the number of cycles after reducing CPI of B and instruction of A is going to be here. So CPI of A is 2. And the total number of instructions is now 40% of instruction count was the number of instructions before. And then we divide it by 2, right? To give us 50% of what it was before. And then we have our CPI of 3 for B. Instruction count for B was not affected, right? And we get 2.2 times instruction count. And again, clock rate was not changed, right? And now we have calculated the instruction count difference here by having the relative instruction count. Okay, so the old instruction count number will cancel, and we get our overall speed up of 1.45. And then if we want to calculate CPI, we have clock cycles, we have instruction count new. So this is our clock cycles, right here. And then instruction count new is 0.8, so 80% of the old instruction count. Okay. Because we basically removed 20%. So CPI new is 2.75. So this is just a recap, right? So we have our performance equation. This is the most important equation from this chapter. Instruction count times CPI times cycle time is CPU time. And then we need to be able to break down clock cycles with this summation formula, as well as CPI using that same summation formula in a different form. So, recap here. So instruction counts, CPI, and clock cycle present different trade-offs. So there are two different kind of large classes of ISAs. There's RISC, which is reduced instruction set computer, and the instruction set architecture that we're covering in this class is a RISC instruction set. ARM is a RISC instruction set. So they're very simple, very high instruction counts because they're simple instructions, but much lower CPI per instruction. CISC. So an example of CISC or complex instruction sets is going to be x86. Okay? Like I mentioned, x86, you can do matrix multiplication with one instruction, right? So they're more complex. They have lower instruction counts because you have these more complex instructions, but they have much higher CPI. And in the end, we're moving more and more towards RISC because due to these very complex instructions, the microarchitecture is very complex and it's very hard to optimize. Especially when you have not just one complex thing to implement, you have thousands of different complex instructions. And like I mentioned before, even x86, they end up being more like RISC because the first few stages of the pipeline in Intel and AMD processors is converting CISC instructions into RISC-like instructions. Okay, so this is your reading, and I just want to finish off with, if I post something on Piazza and it's not there on Canvas, do just let me know. It's no problem, and it actually helps. Okay.
Yes.
I'm thinking this one and one other.